What's going on, YouTube? Hope everyone's having a good summer. I know it's been hot recently. Not a bad idea to crack open a cold one. Keep you cool and refreshed. Anyway, all seriousness, all jokes aside rather, hope everyone's having a good summer, staying cool, being safe out there, man. Don't be too much of a knucklehead. Been busy, man. Been real busy. Let's see if I can clean the camera. Got some good news. Got my bell housing in. Obviously, you can see that. So mine is QuickTime, obviously. It's made by Holley. Check it out right there. Not a cheap piece. About $700 for this bell housing. You can definitely go OEM, and it might not be a bad idea. It's my first time doing a build like this, so this is what they recommended off of, like, I think Jegs is where I ordered all this stuff. So this is their recommendation between the LS and the T56, and it mounts up. So, and it's SFI 6.1 approved. And I'm not entirely sure what that means, but basically, if your clutch explodes or your flywheel explodes, it'll this bell housing will catch that debris, so it doesn't cut your legs off. Because you got to think, when you're driving, engine's up here, your legs might be out here. The clutch explodes, boom, your legs are gone. So that's why that is important. This is steel as opposed to the probably aluminum or cast aluminum or cast iron that the factory bell housings are. So you can see it's got a backing plate right here. That guy, I got that put on. Just a fun fact, you do not have to take the clutch off to get that on. If you guys remember my previous video, I had my clutch already installed because I had it sitting there and I wanted to get it knocked out, and I did. But obviously I didn't have my backing plate on. But all you have to do is take off the oil pan and you just tilt it up at an angle, and then you're going to slide it over onto the back of the engine there. And it's actually, your clutch has to be in a certain position because it's got a cutout. It's got like a half moon cutout here at the top, and you'll see it when you get it, if you do get it. But what am I doing today? At the moment, I am working on checking runout of the bell housing. Holley actually makes a machined piece that mounts on this flange right here, and it's intended to be a precision machine piece that has an opening right here that is within a given tolerance, and it mounts up with these bolts that are on the existing bell housing. Obviously, this bell housing has been coated with something, probably powder coat, and you can see in the surface finish there's variance. So what I'm using is a dial indicator here, and it's broken out into 0.001 inch, which is a thousandth of an inch. And obviously it's got two arms you can use, and then this is a little lever. Like if you you can see how it's got the it's basically a brake in here with a spring, but you can see you can see when I turn it, it'll either bring that in, might be hard to see, or bring it out, and you'll see the dial indicator start touching the surface. Yep, there it goes, and you can dial it in as required. We'll go ahead and get this set back to 0. And this is a magnetic dial indicator. Mine is stuck on the face of the pressure plate, and it's just got a little twist knob. You can twist it on or off, and it just pulls the magnet inside or outside of the base, and it'll attach or detach as needed. But you can see I got mine set to 0. And you're probably wondering, why would I do this? Reason being is obviously this motor would redline 6,000 to 7,000 RPMs. That's pretty standard. This clutch is obviously attached to that, and when the transmission goes into the splines of the clutch disc and the pilot bearing, in the back of the crank, it's critical that it is in line with the crankshaft. So we'll talk about like exaggeration here. If this if this light is the input shaft of the transmission, what you want it to be directly in line with the crankshaft. And if it's and you want it in multiple different ways, right? When you talk about aircraft, you have roll, pitch, and yaw. And here on this bell housing, we have obviously X, Y, and then we have, you know, I guess this would be, that might be pitch. Roll would be this way, which doesn't necessarily apply because the the dowel pins and the screws will take care of the roll. And then you have the yaw, which is this way, right? So you have all these different axes that you're working with, and inevitably, just like we saw, this paint finish or surface finish has some variance in the finish, and you can see it with your eye. You know, there's going to be some, it's called tolerance stack up, but there's going to be some stack up of out of spec measurements that are going to be going on in this whole setup here. And that could be due to the machining tolerance at the factory that they build this. That could be due to variance in the paint. That could be due to variance in the thickness of this flange. It could be variance due to foreign material between the mounting surface of this flange and the engine block itself. It could be a number of things. So it's important to keep that in mind. Now, I guess now that we kind of understand like what am I actually doing here? I'm measuring runout or measuring specifications or tolerances in these given directions. But why is that important? Well, it's important because, like I said, you want the input shaft to be directly in line on all axes with the crankshaft because they're essentially touching each other. And then this clutch pack is, spinning with them together. So on extreme cases, your input shaft may come like maybe like this, right? And your bearings inside the transmission aren't designed to take loads like that. I think there's a few different kinds of loads that bearings can take: normal loads, tangential loads, thrust loads, and then I don't know, I'm sure there's others, but you can look into those. But different bearings are designed to support different things. A thrust is something going down, is a force being pushed down a shaft. Like if this was the shaft, the thrust would be this way. And certain bearings are built to take up that force. And I think the T56 Magnum does have those. I think they call them taper roller bearings, but they do have those bearings in there. But you know, it's only within a certain tolerance, right? It's okay to be, and the specification is that the position of this bell housing relative to the crankshaft can only be 5 thousandths in either direction, and that could be a combination of directions, which is why we take these 4 measurements to take into that account. Have a sip of my beer here. So another thing is Tremec won't warranty your transmission if you don't do this process. Now, I'm making a video, so I'm obviously providing video evidence of what I've done. However, it's good practice anyway, right? No one wants to get on the side of the road, have your trans in the car, and you can't shift gears. Gears are binding up, you're burning up your input bearing, you're burning up your pilot bearing. You don't want to deal with that, right? That's why we spend good money on good parts, so we're not stuck on the side of the road with Chinese junk. But funny I say that as I use a digital angle. Goodness, I forgot the name of it. Dial indicator, magnetic dial indicator. That's what it is. Sorry about that. But anyway, so what I'm doing here is I have my 4 positions. This is where I zeroed the digital dial indicator or magnetic dial indicator, and then basically from here we go to our 4 aspects. And basically what we're checking is the location of the bell housing relative to the output shaft of the crank, or the crankshaft, because you want those things to be in line. Remember, I said that there's you know, it's basically touching. You don't want any different loads on that on the transmission input shaft. So that's what I got going on. The allowable spec is 5 thousandths in either direction. So let's say I have I zeroed this out here. Let's say I measure at the 12 o'clock position. I measured 10 thousandths. So you would basically subtract this from this. In my case, I zeroed down here. I had 10 thousandths up here. So you would be 10 thousandths up in this direction, depending if it's positive or negative, based on the dial indicator. And that would tell you your bell housing is slightly up this way, or it could be slightly down this way, but it's off in this axis. And basically what you would end up doing is there's these dowel pins right here, you can see, and what those do is locate the bell housing relative to the engine. And these are removable. They do make offset dowel pins, and basically you can rotate them similar to how this pen has this notch here, or to the clip. It's offset in that regard, so you can rotate these dowel pins in a given direction to relocate this bell housing. So you can shift it up based on your new dowel pins, shift it left or right or whatever the case is, based on the out of tolerance of your bell housing here. So we talked about the y-axis. In my case, I was minus 3 thousandths in this axis. I was 0 down here, that's where I zeroed it, and it returned to 0 as I rotated, so it's good. And then over here, I'm 1 thousandths, and I'm also 2 thousandths on this side. So basically, it's this one minus this one. You have the negative minus another negative is positive, so it's like negative 1 thousandth off, basically in that direction. And I think I did that right. I'll check my math later, but over here we have 5 thousandths, and the same would apply. But like I said, basically, if you had a 10 thousandth measurement here, a negative 0.010, you would divide that in half, because this dial indicator can only measure its position, connected to this relative to this. So you would divide it in half, because you don't want to move the whole bell housing, the change in this measurement. Because if we moved it 10 thousandths, we would have 10 thousandths down here, we'd be off again. So you would divide it in half. So if 10 thousandths showed up here, you divide that in half. So you're at that point you're out of spec 5 thousandths in that scenario. So hopefully that makes sense for you guys. I know it's a little bit convoluted and kind of confusing, and I know a lot of guys say, well, it's a QuickTime bell housing, maybe you don't have to do this, but I mean, it's probably good practice, right? Guys that turn rotors in the mechanic shop, they have specs they have to follow for runout. This applies just the same. But yeah, hopefully that was informative. I've been goofing around with this mostly. I'm going to try and finish this up, and then the next step I have to do is get my trans, and then mount it up, and then I can start doing fitment in the car. That's really the only update I have for you guys. Once I can get my trans mounted and I'm good with my measurements, I will go ahead and get my trans stabbed, start shuffling this engine over into the car so I can kind of get it positioned in there and see how I like it. And then at that point, I'll have to go out and get a welder, and then I'm gonna have to see about taking my drive shaft, which is sitting right there, over to the machine shop and having them weld on a T56 output shaft flange, or whatever they call it, so I can mate it up to the e38 rear diff. This doesn't necessarily apply to the e38 LS SWAP. This is just something I'm doing because of my application. But if you picked up a 4L80 or whatever with a matching 6-liter motor, you probably don't have to do this, though the factory would have already done it. It's only because I'm using a different transmission, different bell housing, etc., etc. Only other thing I've got for you guys is I did pick up some new injectors. These are made by Siemens. I want to say they're called Deca injectors. I'm not sure if you can see those, that writing there, but these are 60 pound per hour. They are 4-hole injectors. It's a little hard to see in there, but if the camera wants to focus here, of course it doesn't. Hopefully you can see that there's 4 holes in there, but 60 pound per hour. If you're wondering what kind of injectors you need, there's a lot of injector calculators online. I got 8 of them, obviously. If you're wondering what size injectors you need, just go to an injector calculator online. Based on your application, whether you're turbo or naturally aspirated, will change the required output of your injector. So if you're turbo, you obviously have positive pressure inside the manifold. If you're doing naturally aspirated, most of the time you're going to have vacuum. So that change in pressure across the injector will be different. So you're going to need higher pound per hour injectors on a turbo application to make the equivalent horsepower. I'm not sure about that, but if depending on what you want to do, you're probably going to need higher pound per hour injectors, because those injectors are injecting into a positive pressure environment inside the manifold under boost. So just something to keep in mind. Mine are 60 pound per hour, like I said, and I think they were good for, 650 or 700 horsepower. So if I ever decide to get a turbo, which this motor is already forged anyway, it shouldn't be too big a deal. And this clutch can handle, I want to say 600 horse, and the trans can handle 700. So I'd be well within spec for all these components once it's all set up. So I would just have to take the pistons out and open up the ring gaps and then boost it. But yeah, that's all I got for you guys right now. Hope everyone's having a good weekend. Being safe out there. I know it's summertime, it's hot. Stay cool, have a cool beverage on tap. But yeah, have fun, guys, and I'll keep you updated when I can. Hopefully next time you get a video from me, I'll have this kind of sitting in the engine bay. So we'll see.